In this video, we are explaining headroom. Now, before any signal comes in here, let's say VBE, the bias, there's no bias voltage. That means there's no collector current, IC. So what will be the V out? Since there's no collector current, V out is VCC minus 0 collector current, RC. So the collector current is the same as, the output voltage is the same as VCC, which we are taking to be 5 volts. So that is the highest output voltage that we can get. So we are creating our headroom here. Our highest output voltage is 5 volts. We cannot go above 5 volts. Okay, now assuming my emitter voltage, whether the signal or the bias combines, and then the VCC is, so let me take RC to be 1 kilo ohm for easier calculation. So when the VCC, the IC, collector current, which depends on the voltage given to the VBE, becomes as high as 5 milliamperes, then the voltage drop across this resistor will be 5 volts, and then the output voltage will be 0. So that means the highest value of output voltage I can get is 5 volts, and the lowest value when the IC is so as high as 5 milliamperes, depending on the values of these VBE, then I will have 0, because VCC is going to be out is going to be VCC minus 5 milliamperes times 1 kilo ohms, and that's going to be 5 minus 5, which is equal to 0. Okay, so that explains the available headroom. Now we need to consider something here. Remember, our device has to be in forward active region. So if our device is in forward active region, then assuming our bias voltage is 700 millivolts, we do not want our collector voltage to drop below 700 millivolts. If that happens, then it means that our device will gradually be driving into soft saturation and gradually moves into deep saturation. So effectively, our available headroom is such that we do not want this voltage drop to be beyond that, because as the voltage drop and causes the V out to go below 700 millivolts, then our device is gradually moving into saturation. So our effective headroom is no longer between 5 and 700 and 0, but rather between 5 and 700 because of the saturation constraint. Another thing we should also consider is, assuming there is a resistor placed here, then it means that when the collector current flows through this resistor, it will raise the voltage of the resistor, the voltage of the emitter, up. So our available headroom is no longer between 5 volts and 0 volts, but rather between 5 volts and the voltage at which the emitter voltage has been raised to. So supposing the emitter voltage also raises by an extra 200 millivolts, then our available headroom partly is consumed by this raise in voltage, and together with that I might have to add an extra 200 millivolts, meaning that the available headroom should be between 900 millivolts and 5 volts. So we will later look at how the emitter voltage is important and how the emitter resistance helps in stabilizing the circuit, but there's a trade-off between headroom and the emitter resistance. Okay, so we'll keep this short, think about it, and catch you in the next video. Bye.